because this work is done in collaboration with many groups. We have been working, my first, when I became assistant professor in 2003, 2004, I started working on quantum dot physics and application at this time, so it has been a long story for me on this topic. And I will try to give you an overview of what we know and where we are and where we want to go. But today, I would like to acknowledge, of course, John Bowers from UCSB, who is my main collaborator on this topic. Wayne Shaw at Sandia National Labs is also my collaborator on this topic. And I used to work, of course, in the past with some pioneers of this work. Luc Lester at Virginia, when I met him, he was professor at the UNM. Now he's the head of the department of the EC department at VT. And Dieter Wimberg from Berlin, who was also one of the worldwide leaders in this field. You probably have heard about that in 2023, of course, the quantum dot, they awarded from the Nobel Prize, even if we don't talk really about the same kind of application, because these are for more like display, for instance. And what I'm gonna talk today is for devices, for making lasers, amplifiers, maybe modulators. But still, you can see, and I recommend that you download this review from the Academy of Science, the Swedish Academy of Science. It's online. You can download the PDF, and you will see that there are some people like John Bowers and Dieter Wimberg who are actually cited in the references. So it's important that this Nobel Prize actually, for me, give some credit to this field, which is still alive, basically. So I will, of course, mostly focus on lasers, and I like going back to the history and see the main. It's not exhaustive, but you can see the main achievement of the progress in quantum dot lasers. And something that is interesting is, since 1999, some groups, like at the University of Michigan or UCL in the UK, UCSB, University of Tokyo, they have been focusing a lot in trying to integrate these nanostructures with the silicon. And this is actually the key point today I will try to explain. But the first concept, the physics, the concept, the physical concept in using reduced dimensionality for making high performance lasers was introduced by Professor Arakawa, who is actually here, in 1982 from the University of Tokyo. Okay. In terms of companies, there are companies selling lasers, these quantum dot lasers. The first company was actually created in the United States by Luc Lester in New Mexico. So that was Zia Lasers. And today this company does not exist anymore. It has been merged with Inolum, and Inolum is still existing, and you can go online and buy some product based on quantum dot solution. And you have the company from the Japanese team, and it's still also accessible online, Quantum Dot Laser Company, and you can buy product on Quantum Dot. First, I would like to show you something, just to clarify from the beginning what, in fact, what kind of limitation you have with quantum dot lasers. Because at the beginning, people, including myself, we were doing research in trying to use quantum dot to replace the quantum wave for high-speed lasers. And many people in the world, they got some fundings for developing research, for developing high-speed lasers made with quantum dot technology. However, today we know that it does not work for direct modulation. If you want to use direct modulation for QD lasers, we know that it does not work. And it's very easy just to compare. These are the best probably modulation response achieved with the quantum dot lasers. It's fabricated by Peter Hetmeyer in Germany, and it's actually a recent result, and they achieved 17.5 gigahertz. To my understanding, to my view, to the best of my knowledge, this is the best result ever in terms of modulation bandwidth for a quantum dot laser at room temperature. But if you just take a multi-quantum wave laser, it's easy to find tons of papers when you will see modulation bandwidths beyond 30 gigs. This is just an example here. So what we know today is basically quantum dot lasers do not offer superior performance for direct modulation application. We know that, okay? And the reason for that was actually a little bit pointed out long time ago. If you look at these papers published in Physical Review by these two French guys, one is actually professor now, Claude Vesbuch at UCSB in the materials engineering department. They already pointed out in these papers the poor luminescence properties of quantum box system, which is intrinsically limited by the fact that in a quantum dot you have of course the ground state, but you have also some higher energy levels. And basically when you inject the carriers, you have this carrier dynamics from the upper energy levels down to the ground state, slowing down basically the efficiency of the system. That's why it was already more or less in this paper published in 1991. You can bypass this excited state if you want by using an injector. And this is what Pallab Bhattacharya and Sasan Faspur proposed a few years ago at the University of Michigan. So you have your quantum dot here with the ground state, first excited state, first and second excited state, and you put an injector on the side, and then you can inject your carriers into this quantum wave, and basically you try to inject your carriers directly to the ground state of the quantum dot. Then you bypass basically the higher energy levels, but at the price, of course, of higher complexity. And they measure modulation response and performance much better, of course, like for instance here, almost 25 gigahertz modulation bandwidths for their quantum dot laser. It works, but of course it's much more complicated than just using a quantum dot. Okay. So these are clearly the limitation to me of the quantum dot. So the main application of the quantum dot for me, and actually John Bowers is also really active in this field, is for silicon photonics. Silicon photonics, just some numbers, market revenue is supposed to be close to 55 USD by 2035. And if you look at the distribution, you see that most of the silicon photonic is used for data center transceivers. But you have also some application for long-haul transceivers, optical interconnects, LiDARs, 5G transceivers, and so on. But the most of the funding here is actually the money here is really related to the data centers, and you probably have seen that in Texas, these two companies actually plan a massive 600 megawatt data center campus in Austin. So very interesting. And basically, what you need for silicon photonics is a technology, of course, that will address the increasing demand for bandwidth. You need also to address the problem of the reduction in the power dissipation, size, and cost. And of course, you need also to reduce the network latency. And we believe that the quantum dot lasers and the silicon photonics together, they can address actually these goals, and maybe an ideal implementation for reaching actually this goal for data centers, but beyond that for computer conferences. And something interesting is there is kind of a revolution today. I would say a resurrection, not a revolution, a resurrection of quantum dot lasers. And I discovered this last year in San Diego at OFC, because there was this workshop called Quantum Dot, the Resurrection, organized by the company Alpha. And it's true that today we see that there are a lot of companies trying now to use quantum dot for making high performance devices. And these companies are no longer the standard telecom companies, but these are companies really very close to silicon photonics, like for instance Intel or Quintessence in UCSB in Santa Barbara is using quantum dot. Linewidth is a company in Canada. They develop actually frequency comb quantum dot devices. So you can find now some. Hewlett Packard is also very interested in quantum dot for combs, especially. So you can find a lot of companies now doing silicon photonics and injecting money for basically developing the technology. These are some basically statements from people from these companies, and it's very, I think, promising. Okay, so for instance, Quintessence in Santa Barbara, you see that the Alan Liu is say that they are pleased to combine a quantum dot gain functionality with a tower semiconductor, and they are pushing a lot of effort on this. And Alpha Loom, for instance, said there is no other technology today which can provide the power level of all bound DAB lasers above 200 milliwatt with power efficiency of 20% beyond 100 degrees Celsius, with the ability to operate efficiently up to 150 degrees Celsius, and so on and so on and so on. So you can find a lot of things that shows that the topic is really still alive, I would say. So for those who are not familiar, I would like maybe just to introduce a little bit the fundamentals, and then I will try to address all these points, why they are so nice. Because for spatial and thermal efficiency, because you can address broadband optical amplifiers, lasers on silicon, feedback immunity, spectral line widths, potential for squeeze light, and frequency comps. So I'm sure as there are some students in this room, you have already solved this problem of a particle in a box. So you just take a box and basically you solve the Schrödinger equation, and you see that you have quantization of the wave vector and of course of the energy, and you can demonstrate that the energy is quantized, and it's inversely proportional to the square of the dimension of your box. Why I'm saying this? Because we are dealing with quantization. Okay, when we use lasers, bulk, quantum wave, quantum wire, quantum dash, quantum dot, these are the consequence of the quantization. And the quantization is useful for what? Because it's useful because you can, in terms of a device, okay, if you want to make a device, you control the shape of the density of states. So the spectral width of your gain, you control the number of states, which is, for instance, for the laser directly connected with the transparency current. You control the carrier confinement, and you control the tuning, the energy tuning, which is the wavelength. So in terms of number, what do we have in mind if we want to observe this quantization? You solve this equation, this problem, and you know that the energy is quantized, and basically the difference between two energy levels is inversely proportional to L squared. Then you postulate that this difference is greater than the thermal energy. Okay, it means that you have, of course, a quantization which is much stronger than the thermal energy. And if you replace this equation into this one, and if you manipulate some a little bit, then you can show that L is below 30 nanometers if you consider electrons in gallium arsenide at 300 Kelvin. Just to give you an order of magnitude, your L should be lower than 30 nanometers if you want to start observing, of course, the quantization. And this is typically the size, actually, of when you grow the quantum dot, that's what you get. This is what you achieve by molecular beam epitaxy. So typically the width here is 20 nanometers, something like this, and a few nanometers in height. It's more like a pyramid. It's not really a box. but this is typically the shape you get when you do this by MD. When you reach this case of growing dot, of course we talk about zero-dimensional nanostructures, and we talk about semiconductor atoms. These are semiconductor atoms, so in theory you don't have bands anymore. Okay, that's why basically you have only discrete energy levels like here, ground state and excited state. And this is also the consequence of shaping the density of states that brings you to a delta-like function for the density of states, like what you have here. However, this is kind of an ideal picture, because if you do, for instance, if you want to use this quantum dot for, I don't know, generating polarized photons or a single, as a single photon emitters, for instance, that's okay. But if you want to make a laser, of course, you understand that you need more than one dot. So what I'm saying is this picture where you have this Dirac function for the density of state is an idealized picture, which is no longer true when you move to a device, I would say, okay? Because making a quantum dot laser will require many dots.
Hey, are you directly imaging atoms in that picture? On that top?
It's kind of an atoms in.
No, but I mean, I see on the side, on the facet, are those individual atoms being imaged?
This one?
Yes.
Yeah.
That's impressive.
Yeah, that's.
You can almost count the number of atoms in that.
Yeah. That's right. Yeah. So the way usually people do the dots is either by AD or MOCVD. You have in this table here some main demonstration, and typically the way you do it is you take a material 1, you take a material 2, and of course you have a lattice mismatch between the two. For instance, if you consider indium arsenide, indium phosphide is 3%, or if you consider indium arsenide, gallium arsenide is 7%. Okay, so but basically what you have in both, when you do MDE, for instance, you take advantage of the stress relaxation, and basically the nanostructures, they will pop up by themselves. Okay. What is the main consequence of that? The main consequence is it's impossible to control the size. So you will have a dispersion in terms of size, and that's kind of I would say not a drawback, but this is a key point where you need to control the size, but it's impossible to have uniform dot at the end. So you will always have a dispersion. This is an example of what they do at UCSB. Very nice quantum dot, indium arsenide, gallium arsenide, and you see they look uniform, but the uniformity is very high, but of course, it's you always have a dispersion. Okay. They do also MOCVD now at UCSB in Jonathan Klemking group. This is an example. This is very recent. You can take a look at some very recent conference paper. I think in Clio, they started looking at MOCVD. Basically, the way you have to deal with epitaxy is you have every parameter matters, the temperatures, the growth rate, and so on. And the problem is, most of the time, you have to navigate in this two-dimensional space. So what I'm saying, especially with indium phosphide, if you don't pay attention, you can actually have real dots, but you can also end up with more like spaghetti or quantum dashes, which are nanostructures, but with a few hundred nanometers long. So that's different. Which means that the density of state is different. Okay, if you have dots, the density of state is, as we say, delta-like function. But if you have quantum dashes, you see the density of state is different. So there is a trade-off here. In epitaxy, of course, the challenges, and this has been developed by the two groups in the world, mostly UCSB and also in UCL in London. It's the epitaxial growth on silicon. And of course, when you grow stuff on silicon, you know that you will have some issues because you will have to deal with density, dislocation, cracking, antiphase domains. This is typically what you have to deal with when you want to grow say, 3-5 materials on silicon substrates. And something interesting is when I was preparing this lecture, I took a look in details at the background, and I found this paper published long time ago in 1996, again by Klaus Weschbus and Jean-Michel Gérard, and they published this applied physics letters where you see the title, Inger-Massey column boxes, highly efficient radiative traps for light emitting devices on silicon. And in this paper, they say that the efficient carrier capture by Inger-Massey quantum dot combined with the localized nature of excitance hinders the carrier diffusion toward dislocation, and basically they came up with the conclusion that quantum dots are the best candidate for making light emitting devices on silicon. It was in 1996, and they measured, for instance, the photoluminescence of quantum dot on gallium arsenide, quantum well on gallium arsenide, quantum dot on silicon, and quantum well on silicon. And basically they observe that if you grow on silicon, the PL remains better than if you don't, if you use quantum well. So if you use quantum dot on silicon, the PL is better than if you use quantum well on silicon. And a few years later, in fact, UCSB actually reintroduced this concept. You can look at this paper published in Photonic Research or in ACS Photonics, and in fact, you will see this plot where you see the comparison between the quantum well and the quantum dot. And you see that when you do quantum well on gallium arsenide, you get this, but if you do quantum well on silicon, it collapses. And if you replace the well by the dot, you see that when you move to silicon, the PL actually remains pretty good. So the quantum dot, indeed, they are very good for making devices directly on silicon. And we can understand qualitatively this concept by looking at this picture here. If you have this active region made with quantum well and having dislocation, it's true that you are sure that you will have dislocation crossing the active layers. That will, of course, cause a lot of damage on your photoluminescence and your luminescence. But with dot, in fact, the consequence is actually weaker in the sense that because you have a lot of nanostructures, even if, for instance, you have a dislocation crossing this nanostructure here, you still have a lot of nanostructures that don't see the dislocation. So at the end, qualitatively, you can understand that, yes, quantum dots are indeed better than the quantum wave when actually you want to grow directly on the silicon. One point that is really important to keep in mind is, as I said, you need a lot of dots for making a laser. So, which means that when you do the growth, as I said, most of the time you have this dispersion between the quantum dots. So this picture here, where you have, for instance, just a single line, a delta-like function, for instance, for the ground state, is very ideal. In reality, what happens is basically because you have dispersion, you will have many lines. Okay, so you have different dispersion of the ground state energy levels because you have many dots with different size. And of course, each line has also a dependence with, for instance, the temperature, because if you change the temperature, this line actually will be broader because you have, of course, you have the limitation. You have the limitation of the level itself, of the ground state level, but also you have the interaction with the acoustic phonons. You have the interaction with the optical phonons. So which means that when you raise the temperature, you will observe actually a broadening of each line. And in fact, if you look at the basically the consequence of this is called the homogeneous broadening for one dot for a population, for one dot population. But the total actually gives you what we call the gain inhomogeneous broadening of the system. And you understand that this line width here is very important because when you look at the gain expression of your laser is inversely proportional to this line width. So basically, if you want to make a laser with quantum dot and high gain, you need to control the dispersion and you need to make this width as narrow as possible. That's why it's really important for lasers that you need to control the dispersion. If the dispersion is too large, of course, the gain will reduce, and that's not what you want. So there is a real connection here with expectation in epitaxy, of course. Then you can compensate a little bit by injecting more layers. You can stack, okay? And you can increase also the quantum dot density if you want to increase the gain of the laser. So there is some other possibility to compensate if the dispersion is too large. I like showing this example here. It's typically, the challenges is to control this dispersion like these drops, okay? So, in a quantum dot system, why they are so quantum? Because all carriers are localized strongly. In theory, you expect that the energy of carriers are for discrete delta-like function. There is no well-defined wave vector like in a bulk material, and you have, in principle, a large oscillator strength. And the consequence of that, in terms of properties, you reduce the threshold current, you have a significantly weaker temperature dependence, a broadband gain, reflection immunity, optical reflection immunity, a narrow spectral line. You have property for squeeze light. Interesting, we discovered for frequency combs, and as I said, for making super efficient emitting devices on silicon. Some of the results I'm talking about, they are summarized in this thesis. Bozong is actually a postdoc in John Bauer's group now, and you obtain very nice results in collaboration with UCSB on quantum dot laser on silicon. So it's online if you want to, or if you don't want to, if you don't find it, I can send you the thesis if you are interested. I'm sure you know this picture, so I'm not going to talk about this. I like showing this one. Just in case, so you see the quantization is really full, of course. You clearly see that when you quantize the active region, you really gain in terms of threshold current reduction. So the quantum dot, they were able to show very, very low threshold current compared to quantum wave or to bulk material. In terms of stability, thermal stability, I like showing this comparison from the company in Japan, Quantum Dot Lasers. They compare a quantum dot laser with a quantum wave. It's clear, I mean, that you know, the threshold is quite small and is really temperature insensitive compared to the quantum wave. And when you raise the temperature, you still have very good power, while of course for the quantum wave, you see this decrease of optical power. So you really gain in terms of threshold reduction and thermal stability when you use a quantum dot in your structures, in your active region. Long time ago, also, Fujitsu was one of the leaders in the world for developing a broadband optical amplifier with quantum dot technology. They demonstrated many breakthroughs. This is quite old result, but it's interesting to look at, where they develop what they call a columnar quantum dot technology for developing wide bandwidths beyond 100 nanometers semiconductor optical amplifiers with polarization, sensitivity, and very large OSNR. You can find tons of results from Fujitsu on quantum dot devices online. If I go back to UCSB, they clearly, today this group is really at the top of the field in terms of quantum dot lasers on silicon. We are talking about direct growth on silicon. These are, for instance, a cross-section of the structures they develop, and you have all the AP layers. So the active region is here, and they contain these very nice quantum dots. What they are really achieved by controlling the dislocation is this very narrow PL, line width, typically 20 to 30 millieV, which is very challenging when you think, because you have to keep in mind that we are talking about direct growth on silicon. They achieve actually the best result, to my view, in the world in terms of performance, outstanding output performance for lasers on silicon with extremely low threshold current, close to 5 milliamp, low dislocation density, very high power, output power and continuous wave operation beyond 100 degrees Celsius. And long lifetime is actually very good as well, beyond 100 years, for instance, at 35 degrees Celsius. So these are the best result to me in the world today. Even UCL does not have actually this kind of performance for direct growth on silicon. And Jonathan Klemkin actually, as I said, started an activity on MOCVD. These are very recent results published, as I said, at Clio last year. The performance are not as good as on gallium arsenide, these are gallium arsenide, but these are MD growth, of course, and Klemkin is doing MOCVD growth. You see with some VU silicon. The performance are not as good as what John Bowers has achieved so far, but it's very recent activity, just started. And of course, they claim that it's better than using MOCVD than MDE because it's better for large-scale monolithic integration, so a better compatibility with industrial standards. Don't know if you are familiar with laser physics, semiconductor laser physics, but one of the key parameters of lasers, actually it works also for amplifiers and modulators, but in laser we talk a lot. It's this alpha factor here, the line assessment factor. The French, they say it's Henri factor because they believe that it's a French, but it's not French. So for some reason, every time in France, I have to clarify that Henri wasn't French. And it's actually line assessment factor, or line bonding factor, or phase amplitude coupling factor, but Henri factor is an expression used a lot by the French. So this is typically, the definition is here. This is the material definition. So this is a ratio of basically the variation of your optical index with respect to the carrier density over the variation of the gain with respect to the carrier density. This parameter is important because it impacts a lot, for instance, of the properties. And it's related to the coupling of the gain and refractive index through the Kramers-Kronig relationship. And Charles Henri is very popular because you probably have in mind this paper where he revisited the alpha factor in the context of the line width of semiconductor lasers. And when you measure this alpha factor for instance, a quantum wave laser, you have this variation with the parameter independence, and you see it's typically these numbers. So it's a non-zero parameter most of the time when you measure it. But with the quantum dot, what you expect, because in fact the oscillator strength is very localized at the gain peak. You expect that the alpha factor is very close to zero, or almost independent actually of the pan from the simulation here. And we did the measurement with John Bowers devices, and the result of the measurement is on the right. And these are for the quantum wave, and this is for the quantum dot from Bowers group. And we discovered that with the technology developed at UCSB, we were able to measure a near zero alpha factor for these lasers, and we observed a factor of 10 difference compared with the quantum wave. So there is a clear interest in using this technology for reaching very, very small alpha factor values. And this is very interesting because the consequence of that is, for instance, you can demonstrate that these lasers have a strong optical feedback immunity, and the second is they have a natural narrow spectral line compared to a quantum wave, for instance. And we demonstrated this with John. We compare, for instance, the feedback and the stability of the lasers by putting an external cavity. And these are basically the line of the FP modes recorded in the optical domain, and here this is what you see in the electrical domain. And this is the strength of the feedback from 0 to 100% of light back into the active region. You see that when you increase the feedback for the quantum dot, the lines, they don't change. Laser remains perfectly stable. This is a consequence of the very low alpha factor. And if you do the same for a quantum wave, what you observe is beyond a certain level here, above this, you have this broadening and all these frequencies popping up in the RF spectrum. And this is a destabilization here of the laser beyond this level, which is a critical level. And when you look at the literature, we know that the critical level, this line here, is proportional to 1 plus alpha squared to alpha to the fourth. So if alpha goes to 0, of course this number goes to infinity. So which means that the laser is stable. So that's we demonstrated, including in transmission. Yes?
I'm sorry to interrupt. This is really fascinating, and I've read a little bit about this before. Can you give an intuitive feeling for why this is the case? Why are quantum lasers so insensitive to reflections? Can I break it down to optical absorption spectra and or the sort of broader lower gain? Is there any intuitive way I can grasp onto this?
Okay, so what I'm pointing out here is the fact that this number is very small compared
Yes.
to quantum wave.
Yes.
There are some other particularities. In particular, one I would say is actually the quantum dot laser is kind of a quasi-class A laser, in a sense that if you look at the damping, the damping is actually larger because you have this relaxation, through these energy levels. So the damping is higher. So if you combine the advantage of the low alpha plus the damping, definitely you observe that any kind of these results are very indeed fascinating, but you can find in some other papers similar conclusion. For instance, here Hewlett-Packard did the same investigation with recent devices on silicon. They published some feedback stability of their lasers with quantum dot, and you can find some other like in Japan. I mean, it's something that is known that if you combine the two, the high damping and the low alpha, you get a laser with a high stability. And this is of course important for silicon photonics because you can get rid of the isolator. So for silicon photonics it's very important because we know that making an optical isolator on silicon is possible, but it's not a piece of cake, and the performance are not that great. So if you can eliminate the isolator, and that's why the quantum dot lasers are very interesting, because you can potentially use them directly without isolator in silicon photonics technology. The other consequence is the Linewidth. The Linewidth is given by this expression where you have this extension due to the alpha factor compared to the shallow tones. Okay. So the Linewidth of semiconductor lasers, when you look at the phase diffusion, is driven by two effects: the effect of the spontaneous emission, but also the effect of the alpha factor. So there is a joint action of spontaneous emission event and phase amplitude coupling event.
So if I can ask you another question related to this, is that Linewidth enhancement factor related to how inhomogeneously broadened the dot is?
Yeah.
And so which is better, more inhomogeneity or less to get a lower alpha factor?
If clearly it scales up with, you said inhomogeneous, right? Yeah. So from the simulation we made a few years ago, if I'm not wrong, it scales up with inhomogeneous broadening. So the better is to shrink.
So it is better to be.
Yeah, it's better, and it's actually understandable because if you shrink, the gain is much more localized, and the oscillator strength is really strongly localized at the gain peak. While if you spread out, the index variation will be more important. Okay. So that's definitely very important also to control the dispersion again if you want to reach extremely low alpha, and this is what they achieved at UCSB. I said 10 to 20 millieV line width. When I started in 2004 in my lab, we were at 50, 60 millieV. So clearly, if you shrink the inhomogeneous broadening, you can reach extremely low alpha factor value. So in terms of line width, also you understand that if you minimize this parameter, of course you minimize this number. You can play with the Q factors, with some other, of course, ingredients to reach extremely low line widths. But if you don't want to use artificial solution, the low alpha is, I would say, the natural solution to minimize the line width. Long time ago, Yariv gave this figure of merit for the line width. So you take the spontaneous emission factor and you multiply by 1 plus alpha square, and it gives basically a figure of merit. And we did some measurement on a quantum dot compared to quantum wave. These are the evolution of the line width with a pump, for instance. Similar cavity lengths, okay? Cavity lengths pretty similar, so we are clear on that. And you see that, of course, you have just a few hundred of kilohertz without any artificial solution compared to a few megahertz for the quantum wave. And if you calculate this number, you find 30 against 1.5 for the quantum dot. So the nominal line width for quantum dot lasers is actually much better because also you take advantage of the low alpha factor. Then you can have, of course, some other solutions. So here are some other examples. For instance, 30 kilohertz demonstrated by Redmeyer quite recently, 2022, 30 kilohertz for the Lorentzian line width. This quantum dot DLV evanescent lasers on silicon, 26 kilohertz by UCSB. And this last year, there was this paper from a Chinese group published in Laser and Photonics Reviews, and they demonstrated 1.6 kilohertz at 55 C with quantum dot lasers. Very, very impressive demonstration. So definitely the line width is actually much narrower. Then if you want, of course, to reach line width down to the Hertz level, of course, you need some other solution. So you need to look at where you want to go in terms of line width, what are the scalability and the size and the cost. And most of the time, people, they combine gain materials with injection locking or external cavity-based solution. And typically, one project we have been working with John and Wang Shou is a combination of quantum dot DLP laser, for instance, with the silicon nitride resonators. And from the equation, from the modeling, in fact, we expect that we have this very sharp decrease for the line width down to the Hertz level. When you stack, of course, it depends on the number of layers you consider, but you see that you can really reach extremely low line width and very, very quickly, because you take advantage of the fact that the threshold current density is very, very small for quantum dot material. So the question is how to fabricate this now, and that's another problem. But in principle, from the simulation, if you combine this silicon nitride and the quantum dot DLP lasers, you are in a kind of a self-injected lasers, and you can really go even further. So it's interesting. How much time do I have? 5? Okay, so let me see. Right, I'm almost done actually. Let me see what I can talk about. Yeah, we did some experiment very quickly on squeezed light with quantum dot laser chips. So we know that non-classical state of light, like squeezed light in phase and amplitude, it's very important, especially for sensing or quantum communication. And of course, there are also many papers dealing with this, using Chi2 or Chi3 nonlinearities to generate squeezed light. And what we discovered, in fact, you can use a gain chip as a squeezer. So you can use a gain chip as a squeezer, and you can use quantum dot gain chip to generate amplitude squeezing. And the idea is to really, there are kind of a zoology of the different squeeze state of light you can generate. What we want to do here is to address basically amplitude squeezing. Okay, so basically you generate the light where the noise is below the quantum limit, below the shot noise level. Okay. And these are the experiments we realized by using the quantum dot laser. You see on this graph here the experiment where you have the green. This is a shot noise level here, and the green light, the green plot shows basically the squeezing performance. So it's 1 dB on the detector size. It's not that large. So it means that if you recalculate the squeezing ratio by taking the loss, in fact we did that, and we achieved close to 5 dB by basically taking all the loss from the experiment. And when you, of course, use a single mode squeeze state, you achieve that the G20 should be below the unity when you get squeeze state. That's what we measure. We measure here, and we calculate it also, and we are in agreement between calculation and experiment that the G20 can decrease below the unity when the pump current is high enough. And another point is when you get squeeze state, the photon statistics changes. You move from Poissonian to sub-Poissonian, and we also demonstrated from the simulation and the experiment that when we get the squeeze state, the statistic actually is moving to sub-Poissonian. So we double check with a lot of experiment, not only from the RIN, from the noise measurement, but also by measuring the G2, by measuring the photon statistic, and we are in the process of measuring the tomography of the squeeze state by taking the Wigner distribution. What we demonstrated is squeezing bandwidths beyond gigahertz at room temperature. Squeezing ratio, actually I said 5 dB, it's 3.1 dB, sorry, after recalculating the loss, room temperature. And you see we are here, these are the map of the state of the art, squeezing from semiconductor lasers. And this is a corrected squeezing level as a function of the squeezing bandwidth. And basically we demonstrate it here. Our result is positioned here, so it's very interesting, and I will talk with John Boris in a few days about this result. And to finish, quantum dot lasers are very interesting also for making comps. It's probably the best solution for making comps, integrated comps. There are two possibilities to generate comps. You can generate comps by, for instance, taking this device. You take what we call a passive modular lasers, where you have an absorber and a gain section, and at some position, basically you can log the phases. Okay, so you log the phases, which means that if you look at the time domain, where you have a logging of the different phases, you can generate these pulses. And people have been using a lot all of these. You have many results in the literature. One of the record pulse widths was below 400 femtosecond published in Nature Photonics by a group in the UK on gallium arsenide, but you can find some others. I recommend to look at this quantum photonics textbook in 2024 when you will have all these results in detail. Something interesting is in the recent years, people have demonstrated that you can achieve this also by doing that on silicon. So UCSB demonstrated that you can generate very nice pulses by considering epitaxial devices on silicon again. Something really particular is the fact that you can also have situation where you have locking not of the phase, but of the bit nodes. Which means that if you look at what you will get, you will have nice frequency comp spectrum, but not necessarily some pulses in the time domain. And this is something that is in competition with the quantum dot material. And there has been a paper published in Light Science and Application last summer from UCSB, where they discovered that basically, if you take a quantum dot devices, you can generate amplitude modulation or frequency modulation from the same chip. Which means that when you generate amplitude modulation, what does that mean? you have basically this very nice frequency spectrum, as I said. And if you look in the time domain, you have the locking of the phase and the pulses popping up. But you can also have this region where you have a frequency modulated behavior, and you still have a frequency comp spectrum. You have kind of a locking of the bit nodes with good purity and coherence. But if you look in the time domain, you have no longer pulses, and it's a quasi-CW behaviors. These two mechanisms are in competition in the quantum dot materials. So you can generate AM modulation and also frequency comp modulation. And we have been actually working on the modeling. It's going to be submitted in Clio, where we confirm all these points by modeling with the Sandia National Laboratories. So Hanovus, for instance, is really care about using dot for frequency comps, and typically UCSB is developing terabit per second silicon photonic transceiver systems by using this technology. So you see it's a comb laser here. Instead, what is the advantage of using a comb? Instead of using an array of lasers, of single mode laser, you replace many lasers just by a very nice spectrum like this one, where you have all this line. The most important is the flatness here, of course. And just to finish, something really surprising in quantum dot is the fact that even with a single gain section without absorber, you can generate pulses. So if you use a gain section and if you bias the section, there are some positions where you can generate pulse widths. This is a result again from UCSB on silicon, where they measure 5 picosecond pulse widths on quantum dot lasers directly run on silicon. It's very strange, because in quantum well it's very hard to achieve this. Why do you get this on silicon on quantum dot and not really on quantum well? It's because in fact the nonlinearities, the chi3 in the quantum dot material is very high. Okay, so if you want to generate pulses, you need a way to compensate the dispersion from the material. If you want to compensate the dispersion, there are two options. The first option, if you put an absorber. If you don't want to put an absorber, you need another nonlinear effect. And this other nonlinear effect is actually the four-wave mixing in quantum dot material, which is high. And the four-wave mixing is actually related to the chi3 of the material. And we did some experiment with UCSB, where we compare the chi3 of quantum well compared to quantum dot, and we discovered that in the experiment and in the simulation, that the chi3 is actually, you have a difference of 100 difference compared to between quantum well and quantum dot. So because you have a higher chi3, you have a higher four-way mixing, so therefore you can generate pulses without an absorber in a quantum dot material. So I'm going to my conclusion. So you see that this topic is still alive, especially in the context of silicon photonics. I think it's one of the best, the nanostructures, self-organized nanostructures are one of the best practical application of nanotechnologies that can revolutionize information and communication through quantum mechanics. And you see that it's very important for power consumption, thermal efficiency. You can eliminate the optical isolators. You can have a nominal line with spectral line, which is much better than with any other kind of materials. You can also generate very nice comps. And we discover that there are some very good advantages if we want to generate basically squeeze light. There are some other research. For instance, in the UK, they started a project with me on modulators, developing quantum dot for modulators. But you can also use maybe quantum dot for mid-IR and terahertz optical wavelengths, taking quantum cascade heterostructures with quantum dot material. I would say that do it with dot. Normally, we should have this book in 2024, edited by Arakawa at Bloomberg. And you will have many chapters, including my chapter, where you can retrieve all these results. Okay, and if you need any more information or if you are interested in collaboration in this topic, just let me know. I'm very open. Thank you very much.
Thank you. Real quickly, before we step outside for pizza, are there any questions from the audience? People work themselves up. I guess I can start us off. So, in the beginning of your talk, you talked a lot about the different applications of quantum dot lasers and things like optical transceivers. And some companies have started to go and make some quantum dot laser devices. But we've yet to see wide application of quantum dot lasers in industry. What do you think are the key issues that need to be solved for the wide acceptance by industry?
Clearly, today the path is really integrating technologies. I don't think quantum dot, I mean, you know, as I told you, I can't tell you the story, but long time, I mean, Europe was taking the lead on this technology with on quantum dots, physics and application. My lab is just across the street. You have Nokia Bell Labs. It used to be Alcatel-Lucent, and I spent some time in the Alcatel Research Center. And they were doing stuff on that. And they stopped. And Europe actually has stopped the research. I'm probably the only one in Europe doing still quantum dot physics and application. And they missed the application. They missed totally the application because they were really focused on using quantum dot for high-speed transmitters, for long-haul transmission, direct modulation of light, all that stuff. Okay. And today, Europe is actually, all this research is gone. Where is this research today? This research is in the US, in Japan, and China. And Europe is over on this. And I gave this talk in Nokia before summer. They told me, we will do quantum dot again. And I answered, good luck, because you are 10 years behind UCSB or, I mean, other people in Tokyo, or, I mean, it's over. So the main application of that is really silicon photonics. I do believe that it's the real application. In fact, we found the application. The application is for silicon photonics. Because you can really integrate these chips. They are feedback insensitive. They are very stable when you raise the temperature. And it's gallium arsenide mostly, not really indium phosphide. The real application is with gallium arsenide. So we know that indium phosphide, you have some issues. So you can eliminate that. You can eliminate all the application for modulation. We have good modulators, external modulators. So the application is gallium arsenide and integrated technologies. And I'm really sad that they miss the point because I think it's a mistake at some point when you are a company. I mean, you have a joint lab with CLAT. CLAT is really well known in silicon photonics, and they miss the application, and that's really strange. Computer com, data centers, integration technologies, this system, yes.
Okay, thank you. Are there any other questions from the audience? Okay. I think then it's time for lunch. Let's give one last thank you.
Thank you very much. Thank you very much.